All right, welcome back to doing a quiz review for Calc 2 here. So let me go ahead and share my screen and all right. So we finished problem number 2. Okay, that's a volume of revolution. I'm sorry, you do have to memorize the pi integral f of x squared. The x formula for this, remember f of x is like your r, so this is just pi r squared h, and just remember that it's going long ways, so we are getting little pieces of dx's here and adding them all up. All right, so next one we have is 12.7, and this is L'Hopital's rule. Okay, one big thing about L'Hopital's rule is you have to check. Please check that the function of the limit is going to be an indeterminate form. Okay, the yearbook only uses a 0 over 0 or an infinity over infinity, and I did not color outside the lines. I left it as like this is the difficulty that we're supposed to be dealing with. So I left it like this. Okay, again, not the easiest problem, but not something that you can't do. If you get to an infinity minus infinity, you can't evaluate this. Don't treat this as a number. This is not 0. Okay, so the thing about L'Hopital's rule is you have to check to see if it's an indeterminate form first. Once it is, now you can use L'Hopital's to take the limit. Okay. So do me a favor when you're doing this problem, make a point, check indeterminate form, then proceed to do the rest of the problem. Okay, and sometimes you have to do this more than once. So every time you have to use L'Hopital's, check it, make sure it's indeterminate, and then go forward. All right. And the reason why I insist on this is that I've lost grades over this. So that's the rule. That's how it works. All right. So let's go ahead and do a couple of examples here. All right, what do we have here? We have a limit as x approaches 0 from right here, and we have an e to the x minus a 1 plus x all over. What do we have here? We have x cubed. Okay, so what happens on the top? Well, if I plug in 0, we get 0 minus 1 plus 0. I'm sorry, not 0. We get 1. Oh, I'm thinking e to the x, e to the 0 is 1. 1 minus, and on the bottom we get 0. 1 minus 1, the last time I checked, that's 0 over 0. Check, we have indeterminate form. Okay. Now we're going to apply L'Hopital's. Okay, now this is not a quotient rule, so be careful. Okay, you can include quotient rules, but this is not a quotient rule. We are taking the derivative of the top one, top value, the top function, and the bottom function to see what the trend is so we can apply the limit. Okay, so let's go ahead and apply that. So we end up with derivative of e to the x, which is e to the x, minus, what's the derivative of 1 plus x? Right? Well, the derivative of x is just 1. Okay, the derivative of 1 was 0, so we just have e to the x minus 1 to the x. What's the derivative of the bottom? 3x squared. Okay, and now again, we plug in what is, let's see what happens. If we apply the limit, x equals 0, so we're going to have e to the 0, which is 1, minus 1, divided by 3 times 0 squared. Shoot, we got a 0 over 0 again. Okay, which is an indeterminate form, which means we get to apply L'Hopital's again. Okay, so apply LH. Okay, see what I'm saying is like every time you have to do it, we have to check, right? So take the derivative of the top, that's e to the x. Okay, what's the derivative of the bottom? It's 6x. Okay, and as x goes off to infinity, okay, we get e to the x. Oh, we just did, never mind, just took the derivative. What am I thinking? And as x goes off to, oh, x goes to 0, sorry, we get 1 over 0, okay? Which means we cannot apply L'Hopital's anymore, right? So what we're looking at is what's the limit as e to the x goes to 0? This is a finite value. What's the limit of 6x as 6x goes to 0 from the right? It's going to be an infinite value, okay? So this thing diverges, okay? And that's all we really need to say about that. Okay, actually we could say it goes to positive infinity because we can see what the graph of 1 over 6x looks like. Okay, that diverges to positive infinity. All right, so that is an example of actually that's a pretty good problem. It's not the one I picked, but this would have been a good candidate because you should expect to have to do it more than once. Okay, it's just the nature of how L'Hopital's problems tend to work. Okay, so that one worked out. That was a good problem. All right, I liked it. Let's see here. Let's see. You don't always have to use L'Hopital's, so just to let you know. And you have to be careful when you're looking for these things on the internet because, again, they're usually meant for engineering calc people, which means there are going to be a lot of trig functions in them. And I'm not asking you anything with a trig function. Okay. How about natural log of x cubed, ln x cubed over x squared minus 1. And let's do the limit as x approaches 1. Okay, and is it 1 from the left or the right, or is it just 1? Just 1. Okay. So x approaches 1. All right. So they didn't use parentheses, so I'm assuming that this is a natural log x cubed, okay? Which means we can use this little tricky thing here to say this is 3 times natural log of x over x squared minus 1. Again, when we apply our limit, natural log of 1 is 0, and 1 squared minus 1 would be 0. Hey, it's an indeterminate form, so we're checked. Now let's go ahead and apply L'Hopital's, okay? This is 3 times 1 over x here, right? Divided by, this is limit as x going to 1, okay? Right? And then we have 2x, that's it. Okay, because we take the derivative of the bottom, it's just 2x. Now, let's see what happens when we apply x goes to 1. Okay, so we have 3 times 1, right? 1 over 1, divided by 2 times 1. Oh, this goes to 3 halves. Okay, in this case, we only had to do it once. Okay, but this is why we check. Okay, we don't just keep applying it until all the x's go away. You have to make sure that you have indeterminate form. Okay, so be careful about that. This would have been, I would have, although this is an unexpected problem, I would say this one was too easy. Okay, so I wouldn't have given you this one because it's too much of a warm-up problem, but not bad, not bad. Let's see here, trying to find a good other one here. I want something without trig stuff in it because it's not a good way to go. I'm trying to go with stuff that only used stuff that's problems that you would have seen in your book. And this book kind of goes off the rails pretty quick. It doesn't have good, interesting problems after that. How about that one? Okay, this is a limit as x goes to 3. Okay, and we have of e to the x squared minus e to the 9th, all divided by x minus 3. So we're going to check. E, if I plug 3 in here, right, 3 squared is 9, so we get e to the 9th minus e to the 9th, divided by 3 minus 3. That, to me, it looks like a 0 over 0. So this is indeterminate form. Okay, we're going to apply L'Hopital's. Okay, So what's the derivative of e to the x squared? Well, that's e to the x squared times its chain 2x. Okay. What's the derivative of e to the ninth? E to the ninth is a constant. So we take that derivative, we get 0. What about the bottom? Well, what's the derivative of x minus 3? The derivative of x minus 3 is 1. Okay, so here we have 2x e to the x squared over 1. If we apply our limit, x goes to 3, okay, we have 2 times 3 e to the 3 squared. So that's 6 e to the 9. That's a pretty big number. See, this one would be a good one to pick because we're trying to trick you here, right, with a constant. And 6e to the 9th is a huge number. So if you do this on your calculator, you're probably going to see something like that, you know, something like this on your calculator as it speeds off to x to the 9th. So you're going to think it's an asymptote and you're going to think it diverges because this is big. Okay, so this is another nice problem. Okay, that will, there's a lot of little tricks in here that are going on here, you know, to see whether or not you remember how to do things. Okay, so I kind of like it because it's designed to fool a calculator. I also kind of don't like it because it's only a one-step problem. So if you know what you're doing, this is too easy. But yeah, there's potential. I could pick something like this to say, yeah, that would work. Okay, I might do something like this. Okay, so you have to do it twice. But you know, maybe I don't know. That's still making a L'Hopital, so that wouldn't work out so well. Because the next time you took the derivative, you get like a 1 over 0. It wouldn't work. So no, not quite. Okay, but that's the kind of thing we're looking for. Okay, no problem. Okay, so be careful with that. Again, make sure you check indeterminate form. So your L'Hopital's is check indeterminate form. That's step 1. If you can apply L'Hopital's, which, you know, the whole problem is about using L'Hopital's, so I guarantee you, you'll have to do that. Okay, apply L'Hopital's. Okay, and then repeat. How about that? Let's say something like, okay, and repeat. So go back and check your indeterminate form, see that it is, then apply your limit. If you don't have a limit, if you don't have an indeterminate form, you're going to have to use other rules of limits. Okay, which might just mean direct substitution, which is what I did here. Okay, so that's what you do. All right, last problem is improper errors. Right, I'll pause this for a moment while I find a good one, and then we'll see what we're going to do. Okay, now there are several kinds of improper integrals. So again, I just want to warn you, if you go looking on the internet, finding other ones, these are more geared to the engineering students than to you guys. But you could do the ones what they call type 1 improper integrals. Okay, and that's all your book asks you to do. Okay, so there's my favorite problem is something like 1 over x squared from x equals -3 to x equals 4, something like that. And what it's doing, right, 1 over x squared, something like this. Okay, and the problem is between -3 and +4, which is why I picked 2 different numbers, is that there's a 0 here. So what you're supposed to do is break up, you're supposed to go from -3 to 0 and then 3 to 4. Your book doesn't do this. You never had a chance to practice any problems like this. So this is called a type 2 indefinite improper integral. I will not be asking you one of these. So when you see like you have to break this thing up, this is not something you have a chance to practice. This is not something that our course really covers. Okay, so if you have to stop in the middle, okay, it's not a problem for us, right? We do type 1, which means we're going to do something like 1 over x squared. X goes from like 1 to infinity and beyond. Okay, so if I was going to ask you like 1 to infinity of 1 over x squared, okay, dx, what would go on here? Okay, so the first thing you do, because we don't like having an infinity in our integral symbol here. Okay, so what we're going to do is we're going to say the limit, pick your favorite letter, a goes to infinity, okay, of 1 to a of 1 over x squared dx. Go ahead and integrate this, right? This is the integral of x to the negative 1 dx from 1 to a. You still have a limit, a goes to infinity. Oops, negative 2. Just use power rule. Okay, so this is negative x to the negative 1. 1 to a, limit, a goes to infinity. All right. So what we're going to do is we're going to type that. We're going to say, well, this is the limit of a goes to infinity, negative 1 over a, okay, minus negative 1 over 1. Let me plug in the 1. All right. What's the limit as a goes to infinity? What does this look like? Right? What is 1 over x as x goes to infinity? Right? You can draw the graph. As x goes off to infinity, this gets smaller and smaller and smaller and smaller. 0. Okay? Minus a negative 1, you end up with 1. Okay? That's what you do with this. Okay? If you can't get an answer for this, then it diverges. Okay? So it converges. If you can get a number, it converges. If you can't get a number, okay, and it doesn't mean that it goes to infinity, it just means you can't get a number, okay, then it diverges. So be careful, because again, I'll pull out engineering calculus because that's the easiest one I can think of offhand. If you need to integrate a function that looks like this, okay, for a sine wave, this sine, okay, regardless of where you integrate, right, regardless of where you stop, if we're going to integrate from 0 to infinity, we have a positive area, then a negative area, so it would be 0, then a positive area, so it's positive now, then a negative area, so it goes back down to 0, and a positive area, so it's back up to whatever that is, and then a negative area, so they cancel out, and then positive area, and a negative area, and so on, and so on, and so on, and so on, and so on. This never settles on a value. So even though it's not a very large value, because the best it's going to be is this integral right here, it's going to cancel out, go back down to 0, but this diverges. It's not going to infinity, but it never settles to a value, okay? So that's what we mean by diverge. You can't put a number on it. That's all it means, okay? So can it converge? Can it diverge? Yes, one of those two things. All right. Now, what problem am I going to do for you? These are, there's a lot of notation that's going on, and so I don't think I made the integral that hard, because there's other stuff you have to pay attention to. Okay, so what did I pick? I don't remember what I picked. Oh, that's a good one. Oh, that's terrible. So what if we do from 4 to infinity of 1 over x ln x to the 4th cubed. Yep, there we go. One of my favorite kinds of problems, okay, because this looks, if you're not used to this problem, this is going to look scary. But what we're going to do is we're going to say let u equals ln x du is equal to 1 over x, okay, dx. So let's take a look at what we have here. We have 4 to infinity. We have 1 over ln x cubed times 1 over x dx. So this part here, this is just a du, right? This part here, this is 1 over u cubed from 4 to infinity. Does this look like a scary problem anymore? No, this is a Calc 1 problem. So this is u to the negative 3 integral du. Okay, and I'll say u sub 4, u sub infinity. This is a really fine point because you're not supposed to use the same limits. I would never take off for this. I know some teachers who do, but I don't. I'm more interested in, can you deal with this than can you deal with that? Okay, just remember where you are. Remember like which variable you're integrating against. Okay, so again, chain rule, right? So we go ahead and we integrate. So that's going to be add 1. So -3. If I add 1, right, you're $3 in debt. You pay back your dollar. Now you are $2 in debt. So it's -2 over -2, going from u to the 4th, u to the infinity. Okay. So we're going to say this is -1/2, right? That's what this is. Okay. This is 1 over, what the heck is u? U was ln x. So this is ln x squared. And we are going from 4 to infinity because now we're back in the x world. We can go back to our x limits. Okay. I'm going to do one more thing. I'm going to say this is 1/2, 1 over ln of x squared. Actually, I don't want to do the problem this way because I made a big mistake. See, right now, this would be a C problem. Okay, this would not be the correct way to go. We don't like this. Okay, this is the class where you learn not to do this. Okay, so at this point, I got a D, I got a C, I got to fix it. Okay, so we don't want to write this. We want to write, okay, we want to write limit as, pick your favorite letter. We'll pick D because that's what I could have gotten here. Okay, limit as D goes to infinity of 4 to D of 1 over x ln x. Was it cubed? I think it was cubed. Okay, dx. Okay, now we can go back and do the problem just as we just did. Okay, so that's the only thing that changes, that you have to include this. Okay, you have to include this and then this piece right here. Okay, because we don't want to integrate with an infinity in our integral symbol. Okay, now people do. Once you get out of this class, people are going to do it all the time. Okay, I'm not going to come back and haunt you. Okay, nobody is. And once you've done your how to do this in Calc 2, nobody's coming back for you. Okay, so if you ignore it after Calc 2, that's fine, but we need to make sure you know what you're doing and what this means. Okay, we're not going to put in infinity. This is kind of like one of my nieces got really upset with me because she draws her A's. This is when she was learning how to write. Like, it better look like that because that's in first grade. That's how you write your A. Well, grown-ups have different handwriting. Mine is lousy, but my printed A looks something like this. Actually, that's not quite right, but oh, good Lord, I can't write. Something like that. She was not happy. I get more practice with P's, but there's my P. Not happy at all with me. That would be a marked F from her first grade teacher. Okay, it would be do it again, make it look like it does on the board. Okay, same idea here. Okay, if you don't do it correctly, properly, okay, you've got this weird fancy thing that you're dealing with. It's wrong. Okay, so I'm sorry if you put little hearts over your eyes, whatever you do these days. I don't know, but it's wrong. Okay, I like that. You do an I and you put a little heart. Nope, it's wrong. Can't have it. Okay, it's got to be like this. What do you do in fifth grade? You write the hearts over your eyes. Okay, you're not writing this anymore. Okay, so well, at least back when I went to school, that's what other girls did, was they draw the hearts with the eyes. Okay, so there we go. So we're going to go through the same process. Limit D goes to infinity. Okay, from 4 to D, 1 over x ln, 1 over 1 over ln x cubed dx. Let u is equal to ln x du was equal to 1 over x. Okay. We aren't going to worry so much about, we could change the limits. Let's not do that. So we'll go with whatever u was at 4 and whatever u is at d, limit as d goes to infinity. Okay. And this is u to the -3, that's what this says, right? Times 1 over x dx, that's du. Okay, and integrate as normal, so we get u to the -2 over -2 And we're going from U evaluated at 4, and U evaluated the limit, U evaluated at D. Okay, so this was -1/2. What the heck was U? U was natural log x. So this is ln x to the -2. Okay, and we're going from back to our x values, U to D, limit, D goes to infinity. Okay, so let's go ahead and do this. Let's say this is 1/2 natural log x to the -2 from D to 4, limit, D goes to infinity, right? Change my limits of integration to get rid of this negative sign here because that was in the way. So what do we have? We have 1/2 natural log of 4 raised to the -2 minus the limit as D goes to infinity, okay? And this is 1/2 natural log of D raised to the -2. All right. Now, as D goes off to infinity, what is happening to the natural log? Right? What's happening to the natural log? This is what the natural log looks like. So as D goes off to infinity, right, as x goes off to infinity, then natural log is also going off to infinity, okay? But this is a fraction, so it's like 1/infinity, right? Which is very small, 0, okay? So all we do end up with this, we end up with 1/2 ln 4 to the -2 minus the 0 because that's where our limit is. Okay, so this again converges, right? And that's our value for this one. Okay, so because we have to remember it's 1 over this thing, right? So we end up with 0. And this converges, there's our answer. You don't have to converge if you end up with a limit that's not going anywhere. If we end up with like a 1/x as x is going to 0, well, that function, something like that. Okay, so as it gets closer and closer to 0, it diverges. Okay, so just be careful, evaluate the limit carefully, but that's what I'm looking for. Okay, so make sure that when you're doing this problem, you have changed your infinity or your 0, depending, okay, to another letter. Take that letter to whatever the limit was, that whatever you replaced it with, and go through the problem as normal. Okay, keep the little charade of changing the variable here, and then when you're done, you can put it back in and take your limit, and then be good with it. Okay. If I was really mean, this would have involved a L'Hopital's rule, but I was not really mean, so it shouldn't. Okay, but just to let you know, there's a lot more to it than we could have. So this is just a taste, but they are. All right, so that concludes our quiz review. If you have other questions, please let me know, and I will try to address those so that you guys have a good chance of doing well with this one. All right, so very good, and I will see you after you've taken the quiz.